Neutron stars are amongst the most extreme physical objects in the known universe. Dead stars squeezed into the size of a city on the brink of collapsing down into a black hole. But there's a growing number of astrophysicists who believe that an even more exotic cousin could be out there: quark stars. But do these objects truly exist? What evidence do we have for them? And if they are real, could they be the production site for the most dangerous material in the universe? Self-replicating, strange matter. To understand the quark star, we first have to understand the neutron star. When a star heavier than about 8 solar masses reaches the end of its life, the outward pressure from radiation fizzles out, and so gravity tries to compress the star down into a single point. The core becomes so compressed that it reaches a critical density where it's able to resist further collapse, causing the outer layers to bounce off the core in a dramatic supernova event, specifically here a type known as a core collapse supernova. With the outer layers gone, the core is left naked in space and is called a stellar remnant. If that remnant exceeds about 3 solar masses, then it will collapse all the way down into a black hole. But for remnants lighter than this, they instead will become neutron stars. A neutron star is able to avoid collapsing all the way down to a black hole because it has enough internal strength to resist the power of gravity. But that begs the question, what is the source of this internal force? When the sun dies, it will eventually collapse into a different kind of remnant called a white dwarf, an Earth-sized star fighting against gravity with electron degeneracy pressure. This is a quantum effect where electrons, which are a type of fermion, really detest being squeezed together into the same quantum state, an effect called the Pauli exclusion principle. And it is that resistance to squeezing that will one day halt the sun from further collapse. Inside a neutron star, the pressures are far beyond what electron degeneracy pressure can resist though. Electrons have long lost the battle with gravitational pressure here, but neutrons are stubbornly hanging in there. As another type of fermion, they too have a degeneracy pressure, a quantum resistive strength to further squeezing that in fact is much stronger. Indeed, the pressure here is so high that protons capture electrons and transform into more neutrons, forming an exotic state of matter known as neutronium, hence the name neutron star. Described in this way, it's easy to imagine a neutron star as almost a monolithic, asteroid-sized atomic nucleus in space, but one with a comparable mass to our own sun. In principle, you could even put it on the periodic table, just way down. But really, neutron stars are a lot more complicated than that, and frankly, there is still a lot that we don't know. However, since the pressure decreases from the core as we go out to the surface, then we don't expect the outer layers to be in this same extreme state of pure neutronium. Indeed, we expect a series of layers, including various phase states of neutronium, a crust, and even an atmosphere. The surface gravity is so extreme that this atmosphere would extend barely an arm's length out, and the crust would be a crystallized lattice of ions, held in place by their mutual electrostatic repulsion and, of course, the extreme gravity. Deeper down, we get an ever greater ratio of neutrons to protons, with eventually the spin-half neutrons coupling together into so-called Cooper pairs, forming a frictionless superfluid as well as superconducting currents. Neutronium cylinders and sheets are thought to form down here, playfully known as neutron spaghetti and lasagna, which no amount of bolognese sauce will ever make appetizing. It's a mind-bending environment that of course is all sealed away from us beneath the surface, and so we can only hypothesize about what lies beneath using our understanding of quantum field theory. But we have plenty of evidence for the reality of both neutron stars and black holes. There can be no question that these beasts are real. The superconducting currents generate intense magnetic fields which accelerate particles along the axial poles. If the neutron star's spin axis is oriented correctly, then these beams of radiation will sweep over the Earth periodically, and we call such neutron stars pulsars. We know of so many pulsars that we use them to map the galaxy and even test general relativity. Likewise, there's plenty of evidence for black holes, including direct photos of the damn things at this point. But the real question is, could there be something in between? If we kept spooning mass onto our neutron star, the gravity and internal pressure would continue to rise until eventually the neutronium would be unable to resist further collapse. This is a limit known as the Tolman-Oppenheimer-Volkov or TOV limit. But is the next stage truly a black hole? Or could there be another degeneracy pressure that kicks in and saves it from such a fate? Since neutron stars are comprised of 3 quarks each, 2 down and 1 up, an obvious thought is that perhaps the quarks themselves can manifest such a degeneracy pressure, since they too are fermions. In the same way that individual atomic nuclei were forced together into a neutron soup to make neutronium, here we'd smushed together the neutrons into a kind of quark soup of unimaginable pressure. Not a pleasant place to be. This is obviously pretty exotic. We normally think of quarks as only existing in pairs or triples, known as mesons and baryons respectively, although it has to be said that humans have temporarily forced quarks into more exotic states like the tetra and pentaquarks at CERN. A property of quarks that I really can't relate to is that they hate to be alone, a state known as deconfinement. Take a pair of quarks holding onto each other and try to pull them apart, and they'll desperately cling on to one another using the aptly named strong force. Pull hard enough though, and they'll actually use that energy to create 2 new quark buddies. Hence, deconfinement is really hard. Back when the universe was less than a millionth of a second old, the temperature would have exceeded 1 trillion Kelvin, hot enough that quarks could not bind together and were forced to remain in a quark-gluon plasma state, known as the so-called quark epoch. We've even recreated such conditions momentarily at CERN, but inside a neutron star, deconfinement wouldn't occur because of the extreme temperature, but rather because of the extreme pressure. Smushing them together into a fluid rather than a plasma, these are very different states in fact. So if you've seen videos claiming that quark stars will help us understand the quark epoch, this misrepresents the situation somewhat. But in this picture, we wouldn't expect the entire star to be made of quarks in the same way that a neutron star is not comprised of pure neutronium. Remember, there are distinct phases due to the different pressure gradients. So really, only in the core would we expect to find the kind of pressures needed to create this quark matter state, whereas on the surface, it would really resemble a typical neutron star. Indeed, that's normally what we mean by the term quark star, although some prefer the term hybrid star to be a little bit more specific. In any case, it is a quark core shielded from astronomers' peering eyes behind the veil of a neutron star exterior. So quark cores enjoy a kind of privacy, preventing us from monitoring their behavior, which seems like the perfect segue to thank the sponsor of today's video, that is NordVPN, who can offer you a similar kind of protection for when you are online. As many of you know, I've been working with NordVPN for a while now, but the truth is that I was a long-time customer way before that. Their VPN service is lightning fast, affordable, and incredibly easy to use on any device. Personally, I use the iPhone app, which is particularly slick and simple. All you have to do is just click a country on the map and your internet traffic is redirected there in seconds. So the way this works is that VPNs redirect your internet traffic through a private service rather than your regular internet service provider, and thus it acts as an intermediary, masking your IP address. To me, this is a no-brainer, especially when using public Wi-Fis. They even allow you to stream shows from other countries behind IP blockers, including HD content. Sign up today and get a special discount plus 4 additional free months when using my link at nordvpn.com/coolworlds. That's nordvpn.com/coolworlds, or you can just click the link down below in the description. Plus, it is risk-free with Nord's 30-day money-back guarantee. So please do check them out, and thank you to NordVPN for sponsoring us today. Now, back to the video. So if quark stars are shielded below neutron star exteriors, is there any hope of actually proving their existence? A major difference would be that these quark stars would be denser and presumably more massive than that possible for a neutron star alone, which, recall, is given by the TOV limit. For a cold neutron star, this mass limit is estimated to be between 2.2 and 2.9 solar masses. So, a neutron star in excess of 3 solar masses would be fairly conclusive evidence for our first quark star. But no such object has been discovered. Yes, there are examples with reported masses above 2 solar masses, but none of them definitively violate the TOV limit. But mass alone isn't the only tool at our disposal. There are other tricks for potentially discovering quark stars. In 2002, Jeremy Drake and colleagues suggested that a pulsar called RxJ1856 was simply too small to plausibly be a neutron star, possessing a quark star-like radius of 4 to 8 kilometers. Unfortunately, later analyses revealed that the object was cooler than previously thought, and for a given brightness, that means that the size must be bigger, resolving RxJ1856 to have a more mundane and neutron star-like diameter of 14 kilometers, not 4 to 8. Another proposed strategy has been to look at the temperature versus age of neutron stars, since quark stars are hypothesized to cool much faster thanks to neutrinos. The pulsar 3C58 has been suggested as a possible quark star on this basis, having seemingly cooled too quickly. However, aging neutron stars is incredibly difficult, and a slew of different methods applied to this object have yielded ages differing by almost a factor of 10. A third strategy is to look for neutron stars spinning too fast. Since quark stars are more compact, like an ice skater tucking their legs in, they spin up and they can reach sub-millisecond rotation periods in fact, something thought impossible for a neutron star. In 2007, Karit and colleagues claimed that X-rays from the neutron star XTE J1739 indicated oscillations with such an impossible frequency at 1.1 kHz. But sadly, and once again, independent reanalyses of the same data did not support this result. Time after time, we seem to come across what looks like the first evidence for a quark star to have it unceremoniously ripped from underneath our feet. But maybe we are looking at this the wrong way. Maybe quark stars are not this rare unicorn out there, but instead they are a common state in the interiors of neutron stars, simply the product of a natural phase transition from neutronium to something more exotic. They're not surprising, they're inevitable. Consider that the density of matter inside an atomic nucleus is about 0.16 nucleons per cubic femtometer, but the density at the core of a neutron star is even higher than this, so why should we expect the familiar nuclear forces that operate between nucleons to ever do a good job at explaining neutron star interiors? It's unclear exactly how one defines quark matter, but perhaps a working definition is matter which cannot be well described as a collection of hadrons, which includes protons and neutrons, but instead requires modeling a sea of quarks. The behavior of matter under extreme pressure can be done by considering the so-called equation of state, a mathematical description of how matter responds to different temperatures and pressures. Emilio Nala and colleagues investigated this in 2019, but quickly ran into the problem that the kind of energy densities expected inside neutron star cores are simply impossible to even numerically calculate due to a problem in lattice theory known as the sign problem. However, one can calculate the equation of state for low energy densities where matter behaves just like normal hadrons, as well as the very extreme limit of a pure quark soup where they act essentially as free particles. Anala et al. Then cleverly interpolate between these two extremes in as many ways as they can imagine, but are still physically plausible. This leaves a large number of possible models on the table here, but many of them cannot produce neutron stars heavier than 2 solar masses, which we know must exist because we've observed them out there. Similarly, another set produce neutron stars which are so stiff that they can't squish in the way that we observed in gravitational wave observations. Culling these excluded models, the authors end up with what they claim are the allowed range of physical models for neutron star interiors. Finally, they remove any cases where the sound speed inside this material exceeds 1/√3 the speed of light, which is known as the conformal limit stemming from field theory. So here's the punchline. The surviving lines imply that quark stars must be out there. Yes, 1.4 solar mass neutron stars can get away without a quark matter core, but for the 2 solar mass objects, which we know must exist, their results indicate a large quark core, just over half the diameter of the entire neutron star. So a combination of theory and observations suggests that quark stars really should exist. A remarkable consequence of this is that there should be some neutron stars out there who are teetering on the edge of forming quark cores, but because of their fast spins, they produce a centrifugal support which resists gravity and thus prevents this internal pressure from reaching the critical point. Eventually though, the star will spin down, losing that support and triggering the formation of a quark core. Such an event could even lead to a quark nova, an explosion that would outshine even supernova events. Now at this point we might stop and be happy. Another little scientific curiosity explored. But the mere existence of quark stars opens the door to a very disturbing possibility: strange stars. This, again, is a topic which has been heavily over-dramatized on YouTube and beyond, but together, let's take a sober look at this. In the 1960s, Murray Gell-Mann and George Zweig independently proposed the quark model to explain the zoo of hadrons being discovered in particle accelerators, which gained growing evidence in the years that followed. So we now understand that hadrons, such as neutrons, are comprised of quarks. Specifically for the neutron star, there's 2 down quarks and 1 up. Most hadrons decay very rapidly, of order of 10 to the minus 23 seconds or so, but some take much longer. The lambda hyperon, for example, takes of order of 10 to the minus 10 seconds. Now, when this was first discovered back in 1974, the physicists involved found it so strange that they introduced the formal terminology of strangeness into the particle physics lexicon. It turns out that this stability is caused by the presence of what we now refer to as the strange quark. So, lambda hyperon has 1 up, 1 down, and 1 strange quark, which balances out to an electrically neutral particle, just like the neutron. Now, lambda hyperon might be stable for 10 to the minus 10 seconds, but it's hardly stable on the kind of timescales that we normally deal with as humans, nor indeed the kind of timescales that stars care about. However, in another example of 2 independent papers, Arnold Bodmer and Edward Witten predicted that a uniform mixture of up, down, and strange quarks should become increasingly stable the larger it gets. In fact, get enough of them together, and this would become the most stable stuff in the universe. Broadly speaking, this happens because in a neutron there are 2 down quarks, fermions which cannot share the same state because of the Pauli exclusion principle. As a result, one of them has to be in a higher energy state. But with strange matter, the 3 quarks have different quantum flavors, and thus they can all relax into their ground energy state. Now, it turns out that the energetic cost of converting a single down quark to a heavier strange quark is simply too much for this to be worth it for the lambda hyperon, and hence it decays quickly. However, for a large assemblage, the ensemble would indeed be in a lower energy state even after accounting for the conversion cost to these strange quarks. The more of it you have, the more stable it becomes. It is, in essence, self-stabilizing. Now, the heart of a quark star seems to be the ideal environment to manufacture strange matter, thanks to the intense pressures. Crucially though, if a lump of this strange matter was somehow ejected back into the low-pressure environment of empty space, it wouldn't decay like the lambda hyperon, but instead, it would be completely stable, indefinitely. The idea is called the strange matter hypothesis, and if true, it means that all nuclear matter, including me, you, everything in this room, is not truly stable. We are all metastable to strangeness. By the way, we've even printed that tagline onto a few t-shirts that you can find down our merch store. If so, all hadronic matter, given enough time, will eventually decay into strange matter. However, given that you need a whole bunch of quarks to do this all at once, it's incredibly unlikely in most circumstances, a bit like the probability of all the air particles in the room suddenly rushing to the corner at once. The phenomenology of strange matter was explored in a seminal paper by Edward Fahey and Robert Jaffe, and This paper is frankly kind of extraordinary for some of the predictions that it contains. Thanks to its self-stabilizing property, they predict that strange matter would become stable once it crosses some minimum threshold in size of order of a few hundred quarks, nuggets that they call strangelets. This stuff would be so dense that if you placed any macroscopic volume on Earth's surface, it would immediately tunnel to the core due to gravity. If it is indeed stable in bulk like this, then it should have the disturbing property that upon contact with ordinary nucleons, it would absorb them and transform into more strange matter, yet more doing so in an exothermic reaction. If true, strange matter would be a bit like Agent Smith, going around converting everything around it into more versions of itself. Now, strange matter is mostly electrically neutral, but it can obtain a small but meaningful charge near the surface. Fahey and Jaff find that if the charge is positive, then in a low-energy environment, electrical repulsion should prevent it from ever making contact with atomic nuclei, which of course also have a positive charge. This is really the same physics as to why when you lean your arm on a desk, the atomic nuclei in your arm do not come into physical contact with the atomic nuclei in the desk. The electric fields around each of them are too strong to allow that. However, one exception to this is that neutrons have no charge, so any kind of neutron-rich environment, such as the heart of a neutron star or even a nuclear reactor, would feed the strange matter much more effectively. Indeed, the authors hint that this could fuel a rather impressive energy source for humanity, a strange matter engine. Negatively charged strangelets would be a far more dangerous proposition. Ordinary matter would be attracted to it and then quickly absorbed, turning into more strange matter. I have never seen a quote quite like this in a paper before, so I'm just going to read it out for you. Clearly, negatively charged strange matter would have disastrous consequences for any ordinary matter it touches. It probably could not be tolerated at any level, on Earth or in ordinary stellar environments. So, should we be worried here? Well, clearly the hypothesis sounds pretty terrifying on paper, but crucially, it doesn't seem to fit our observations of the universe at large. Consider that if true, Caldwell and Friedman estimated that essentially all neutron stars would have been converted into strange stars via this process by now. This is because we know that neutron stars collide, merge, and explode in various astrophysical scenarios that would eject infectious strangelets across the cosmos. Indeed, most of the gold on Earth, for example, is thought to have formed from the merger of binary neutron stars. Whatever the electrical charge that strangelets have, neutrons just don't care, and so therefore neutron stars should be rapidly converted into strange matter. But these strange stars would be far more dense and have much thinner crust than their neutron star counterparts. So together, we'd expect to see faster spins, denser objects, and this very thin crust would not allow for an effect called glitching that we see in pulsars. These are small but very sudden jumps in the rotation frequency connected to the crust's inertia. In addition, X-ray bursts and seismic vibrations of neutron stars also appear to indicate a nuclear matter crust, not one made of strange matter. Yet more subsequent theoretical work suggests that even if strangelets were real, they'd most likely have a positive charge protecting them from consuming ordinary matter in most conditions. Again, think why your arm doesn't go through a table. So, whilst the case for some kind of quark core within neutron stars looks reasonable, I think the case for universe-consuming infectious strangelets looks less likely. I know, I'm on YouTube and I'm supposed to sensationalize everything for clicks and views, but the truth is that if the universe were really dangling on the precipice of some kind of cataclysmic event like this, then really we shouldn't be here to talk about it. Nevertheless, these explorations remind us just how remarkable the cosmos is, the staggering diversity of strange objects that are out there, and the rather surprising fact that our small human brains are capable of making sense of any of it. If the universe has taught us anything, it's that we will never run out of new amazing things to discover out there, and that nature's imagination far exceeds that of our own. So, until next time, stay thoughtful and stay curious. Thanks for watching, everybody. I hope you enjoyed this video. If you did, be sure to subscribe. Less than half of you actually subscribed who watch these videos, so please do click that button. It helps us out a little bit. You know, we actually have a podcast as well, so if you haven't seen it already, head to Cool Worlds Podcast to check out some of our recent episodes. And if you want to be one of our supporters to the Cool Worlds Lab, you can do that by clicking the link up above, and you can be headed to a website that'll help you set up a donation. So that keeps the lights on around here, lets me spend more time making videos, so please do check it out. Thanks as always.